Today I'm going to start with where we left off last time. If you remember, we were going through this example. So I'll finish the example first, and then I'm going to switch to lecture mode. So today we're gonna talk about pre-processing the data sets, which is a very, very important step in the machine learning pipeline. Again, I don't think I will be able to finish all the pre-processing chapter. I'll do my best to cover as much as I can. All right. I already shared the link to the material, so you can have access to. I reorganized the folders, so this time you will be able to see module 1, module 2, module 3. I called it module 1, module 3 because I couldn't finish the material from last week. It will be confusing if I said week 2 and week 3, week 2, week 1, week 2, and week 3. Okay, so if you could open this introduction to Scikit-Learn file, which I already shared with you, you will see where we left last time. I think we left right here. So this was the last thing we did, right? We left at step 5. So what we were doing was we were simply trying to get familiar ourselves with the Scikit-Learn API. So in order to continue from where we left, let's just import these libraries first, and then the data set as well. Okay. Yeah, and that's this one. So we are loading the digit data set, which is a small data set for images of handwritten digits, if you remember from last time. And then here we are dividing digits into train and test data sets. I'm just running the parts where we're gonna need for the remainder of this exercise. Okay, so this is where we were training the model. I hope everybody had access to, just 1 second. You don't see the link. Okay, I'll send the link one more time. Yeah, the link is right here. Somebody already shared it. You can have access to link. If you check the chat room, the link is right there. Okay, so what we did was we were training this linear SVC model, remember? And then we ran it, and then we found the accuracy to be 0.94 for the test data set and 0.99 for the training data set. Now we're gonna do the similar thing for random. Okay, so I'm just going to insert this. I'm right here. Okay, I already uploaded the data set or loaded the data set. I already set my train and test data sets. Now I'm gonna do the same thing I did with linear SVC. I'm gonna do the same thing with random forest. Something about random forest, which is a topic of another lecture, but random forest is an ensemble of decision trees, actually, right? So that's why we call it forest. So we have multiple decision trees. And where the word random is coming from, when we create those decision trees, we are creating, for each tree, we are creating one version of our data set by randomly sampling our data points, right? So that is the first randomness we introduced to random forest. Second randomness is when we create those trees for each tree at each split. When we create the leaves of that tree, we are randomly choosing the features, right, that we are going to consider for that split. So that's why we call it random forest. So forest is multiple trees. Randomness is coming from two randomnesses, actually. One is the way we are creating the sampling, which bootstrapping, right? So we are creating a random sample of our data points by replacement. And second is we are sampling the features that we're going to consider for each split, for each tree. So there are two randomnesses And then that's why the name random, right? So then we have random forest. So random forest is a nice algorithm to use for as a baseline model, like a benchmark. One thing that I always say is if you are going to solve a problem using machine learning, the first thing is after you clean up and then do the pre-processing on a data set, please choose an algorithm that's gonna work. So have a model that is working and then use that as the baseline model and then try to beat that model by a better one. Better means in terms of accuracy, in terms of, it depends what kind of metrics you are using. Accuracy is very important, but then the model should not be taking too much of computation power, right? So you have to consider different aspects of the problem. Random forest is a nice benchmark to begin with, okay? So please choose the simpler and working models first, and then try to beat that model. Okay, so for random forest classifier, we are going to first import it from Scikit-Learn ensemble. Again, as I said, random forest is an ensemble model. So I'm going to import random forest classifier. So this is a classifier algorithm. I'm using a classifier algorithm because this is a classification problem, right? Because my data set has 10 categories. I'm trying to estimate which category a test data point belongs to, right? So this is my random forest. Let me just run this. I'm importing my random forest classifier, sorry. And then I'm going to instantiate my model. Let me call my model as RF. So I'm gonna instantiate a random forest classifier. Normally, I need to enter my hyperparameter values here, but for now, let's just use this parameter. And if you ask me why you are using 50, 50 is number of the trees, number of estimator, 50 is the number of trees that I'm gonna be considering for this model. For now, just let's say that 50 is a good choice. This is a hyperparameter that you have to tune up to increase the accuracy of the model, but let's just use 50, okay? So now I instantiated an object from this model. RF is my estimator, okay? The next thing is I'm going to fit my estimator on my trained data set. Okay, so this is my estimator on my trained data set. Okay, so it's a random forest classifier that is fit on my trained data set with 50 estimators. And the next thing is, again, it's I'm gonna use the same object, which is RF, which is now fit, right? It is ready to be tested on my test data set. I'm just going to check the score on my test data set. Okay. Okay, so this is the score on my test data set. So you can say so you can just put this into a better, nice looking format. For this. So it's 0.97. Let's also print the train accuracy, right? Okay. So again, train score is 100% and test score is 0.97. So there is overfitting here, right? So we have to take care of. Again, remember overfitting, our model is fitting perfectly to our train data set. And then our test score is less than our train score for our training data set. So this is some indication of overfitting, which we may have to take care of it. It's a topic of another discussion, but just for your information. As you see, random forest is doing slightly better than linear supervector machine, right? Which we used last week. Okay, so far we just implemented two very simple implementation of two algorithms, classifier algorithms for this data set, supervector machine and random forest. So next thing is we are going to do cross-validation. Again, remember what cross-validation was. We are going to divide our data set into three pieces, this time train data set, validation data set, and test data set. And not only we divide our data set into three pieces, but also we are dividing, when we are creating train and validation data sets, we are going to do this in a different format. We are going to create folds of the train evaluation part of the data set. And then if there are 10 folds, each time one of these 10 folds will be the validation data set. The remaining 9 pieces will be the train data set. Again, remember from discussions from last week. So I don't want to take too much of your time by repeating what we already said. But this time we're going to do the similar things using cross-validation. Okay. When I say similar things, I'm going to be running the K-neighbors classifier in this case. Where is it saying K-neighbors classifier? I'm going to be running K-neighbors classifier in this case. You can run different algorithms, but let's begin with K-neighbors classifier. Again, for this, we need to first of all import. I see some questions. Yeah. So number of estimators 50 is number of the trees that I will be using for my random forest. Okay, number of estimators. Each tree is an estimator. Okay, so let's. I'm going to import cross-validation score. Okay, cross-val score. Okay, so for this example, let's use K-neighbors classifier, which we learned last time. So that is Scikit-Learn neighbors folder, and then right. So this is K-neighbors classifier. All right. So let's just import these two. It should be double S in here. Okay. Now I am going to write my cross-validation score. So this is the class cross-validation score. This is going to allow me to create validation and test data sets. Not only that, but inside the validation data set, I'm going to create folds. Okay. All right. So for this, first of all, you need to put your estimator, K-neighbor. Okay, this is your estimator. Well, if you like, instead of doing this, you can simply say K-neighbor classifier equals this. Again, and inside this, you can say KNC. Okay, KNC is the instance of K-neighbors classifier. You can do it this way or this way. Both way will work. Okay, K-neighbors classifier, and then I already have my X train, right, and the Y train, right. So what I'm going to do is I'm going to split my X train data set into folds, right, and how many folds? Cross-validation folds. I'm going to be using cross-validation on, in this case, let's say 5 folds. Okay, and also let me say scores equals cross-validation score. And not only that, let me also print these scores. So the scores variable is going to hold the mean score, okay? It's going to hold the score, I'm sorry, it's going to hold the score for each model. I'm going to create 5 models, and for each model, I'm going to have 1 score, and scores will be holding the score for each model. Right? So these are the scores for if you want to simply right. For this you need to so this is the mean score of 5 scores. Why do I have 5 scores? 1 score for each fold, right? 1 score for each model. Each model has 1 fold as test and 4 folds as a trained data set, right? So, and then for each model, my test data set will be a different fold, right? Okay, well, we can put this a little bit in a fancier format. Okay, let's print this. I'm just going to say accuracy, okay, is this, okay, is this. So let me just use 2 decimal points. And then I'm just going to write the 95% confidence, right, for this accuracy. So more or less 95% confidence. So let me use another placeholder. So these are placeholders, right? Okay. So this is the first one will be the placeholder for the mean score. The second one will be the placeholder for the standard deviation, right? So let's do this format. Okay, so the first one, the first placeholder will be for the mean of the scores. So let's use this MP mean of the scores, okay? And the second one, this guy, right, will be for the, this time scores has standard deviation method. So you can do the same thing for here, actually. Let me show you that one too. You can use NumPy or you can directly use scores.mean. Both will work, okay? Both will work. Okay, standard deviation, because it is 95% confidence, let me take twice the standard deviation. Okay, so did I miss any parentheses? I hope not. Let's see. Right, so this is, again, the accuracy, 98%. It's the mean of these scores. The second one is the standard deviation of these 5 scores times 2. Why did I take 2? To create percent confidence interval for the estimated scores. Okay. All right, so this is the let's do one thing different now, next. But then let me check if you guys have any questions related to the topic. Yeah, so this is the, I hope everybody has access to the class material. Okay, so let's do the same thing one more time, but this time, you see here I used cross-validation equals 5. When you are using cross-validation for inside cross-validation score, which is coming from model selection library of Scikit-Learn, by default, you are using K-fold. Okay, what is K-fold? What you are doing is you are dividing the train evaluation data set into 5 pieces, 5 folds. So let's do this a little bit differently. The same thing, but a little bit differently. So let me use 10-fold as following. Okay, so again, this time I'm gonna be importing K-fold and stratified K-fold explicitly, okay, from Scikit-Learn's model selection. Okay, model selection. I'm gonna import K-fold, which by default I have been using here. Okay, and stratified K-fold. Why stratified K-fold I want to use? Because this is a classification algorithm, and when I'm creating my folds, I would like to have the same ratio of label values for each model. Okay, so that's why I'm using stratified K-fold, and then I just wonder if there is going to be any difference in terms of model accuracy. Okay, so let me run this. So now I imported K-fold and stratified K-fold. Now I'm gonna do the same thing. Let me just, if it is okay for you, let me just copy this. And you can also copy. So let's just, okay. And this time I'm just going to say CVK, okay. This is K-fold equals, right, K-fold. Then you need to say how many splits, and number of splits is 10, okay. And that's all use the same random state. Random state is, remember that it's a seed number, so that we all will have the same splits. All of us will have the same splits. That's why I'm using random state. Okay, this is my K-fold object. Let's do the same thing for stratified K-fold. Let's call this SK, but this time this is stratified K-fold. And I have the same number of splits. Okay, so let's call this scores K. Okay, and CV equals, instead of 5, CV is name of the parameter. The argument for this one CVK. Okay, and I'm gonna do the same thing again. Let's call this SK, and CV equals CVSK, right? So I'm doing exactly the same things, but I just changed my number of splits. And this time I have K-fold and stratified K-fold. Again, remember, the difference between these two is with stratified K-fold, when I create the folds, for each fold, I am maintaining the same ratio of classes, right? Same ratio of classes means I will have the same ratio of digit 1 and digit 2 and digit 3 within each fold. Okay, that is why I'm using stratified K-fold. All right. And then let me also print this for both of them. Okay, so you can do the same thing again. Accuracy for K-fold, for stratified K-fold. And then you need to change this scores K, scores K, scores SK, scores SK. Okay, I hope I didn't miss anything, and let me just run this. Yeah, I got the same results for this example. I got the same results. You might have different results. You might get different results if you, if we have a large data set, right? We might have a different result, but here we got the same results. Okay. So if you guys are ready, we can now go to the next one and then do some bridge search. Okay. If that is okay with you. So we started with running a single model. Then we ran cross-validation score, creating multiple models, right, for each fold, and using each for each split of the data set. This time, I'm going to be using cross-validation score for each value of my hyperparameter. Okay, so I'm going to create multiple values for my hyperparameter, and then for each of these hyperparameter values, or if I have multiple hyperparameters, for each combination of hyperparameter values, I will do this cross-validation score. Okay, what is my goal here? My goal is trying to find the best hyperparameter values for my model. Okay, that is the purpose of grid search. Because this is a simple example, we'll do grid search over all the different combinations of our hyperparameters. If your model is really complicated with a large data set, I mean, doing grid search over all possible combinations of your hyperparameter values will take infinite time. So that's why Scikit-Learn has random grid search in addition to grid search, which you should use it. But in our example, we are just going to use grid search simply. Okay, let me see if there are any problems or questions. CVK is cross-validation for K-fold. Yeah, cross-validation for K-fold. We are setting shuffle to false. So you can set, if you set shuffle to true, then each time you split your data set, you are shuffling your data set. Okay. Let's do the grid search. For that, first, let's import our okay. I will be importing grid. Okay, and let's use support vector machine for this example. Again, hopefully we're going to learn about it later. Hopefully, if we have enough time. Let's use support vector machine. Port SVC. So earlier we used support vector machine with linear SVC. Okay, here I'll be using SVC. So these are two different models. One is a linear support vector machine classifier. The other one is, the real support vector machine. Okay, so which we have to tune up the hyperparameters for its Gaussian kernel, right? And we'll see those hyperparameters in a minute. Okay, let's just import these guys. I'm trying to go step by step, and then whatever we are typing, let's know what we are doing. Okay, otherwise, I mean, it's just a bunch of words we are typing on the screen. Okay, let's define the hyperparameter. I already put the step here. So let's define the hyperparameter. So what are the hyperparameters? To define your hyperparameters, you need to know your model, right? So the model is support vector machine. So this support vector machine SVC has two hyperparameters. One is C, the other one is gamma. So what is C and gamma? Let me use Markdown. So when we are optimizing the model to find the parameters, right? So what we are doing is we are trying to minimize the loss, right, over our data set. So what is that loss? Normally, loss has two components, right? Loss has two components. The first one is I'm just gonna use. It's gonna be a bit tricky. So let me just use. Let me just use this. So if I have n number of data points, right, my first loss component will be, in this case, my true label value, right, which is y, minus, let's call it yi, because I'm going I from 1 to n. My true label value yi minus my estimated value. You'll see the equation in a minute, okay? So I'm using the minimum mean squared, which may not be the best option here, but I'm taking the difference between my true label and my estimated label. This is the first component of my loss function for supervector machine. This loss function has a parameter in front of it, which we call it C. Okay. My second component is the regularization term. Hopefully next week, I'm going to talk about regularization. Next week or the other week, I'm going to talk about regularization, which is the way we are using to reduce overfitting. Okay. And for regularization, C is the hyperparameter. So in supervector machine, C appears in front of the first component of loss function. The second component, let's use L2 regularization here, is going to be, in this case, yi, let's call it square, okay? So this is my, right? So this is my loss function. Let me just delete these guys. So I'm focusing on this. This is my hyperparameter C. What is this C is doing? This C is giving the weight over the first component versus the second. This second component is regularization term. The first component is the difference between my labels and my predicted values. So my goal is I want to do my best to reduce the difference between my true values, label values, and my predicted values. But when I'm doing this, I equals from 1 to n, I have n data points in my training data set. If I only have this first component here, right, then what I'm going to do is I'm going to do my best to reduce this difference over my training data points. When I do my best to do that, then I might train a model that is fitting to my training data set perfectly, or that is, I mean, excessively fitting to my training data set, okay? So when you fit your model perfectly to your training data set, this model may not be working as perfectly for your new data points. So that is, we call overfitting problem, right? To reduce this overfitting, what I'm gonna do is I'm adding the second component, which is a penalty term. By the way, this should also be summation, but so what I'm doing is I'm penalizing my algorithm with introducing the second loss component. Okay, so here C is a hyperparameter which is distributing weights between the first and the second component. If C is high, I will have less penalty on my loss function. If C is low for my supervector machine, I will have more penalty, means I'm gonna have more generalized model, okay? So please just know this much for now, because I'm gonna talk about regularization in more detail later. So this is the first hyperparameter which I will focus on. Second hyperparameter is related directly with supervector machine, which is related to the kernel function. So in that case, I am playing around with my kernel function. And if you ask me what is kernel function, it's a different story. Please wait for supervector machine. I am playing with my kernel function hyperparameter, which is gamma. So what gamma will do is how strict my supervector machine will be in terms of drawing the line in between, in this case, two different classes. So what does that mean? Remember our k-neighbors classifier, when n equals 1, we had those border lines when n equals 1 for the k-neighbors classifier. We had those border lines that was very irregular looking, right? And then trying to fit the model perfectly to the trained data set. So similarly, gamma is like the k-neighbors, number of neighbors for k-neighbors. Gamma is similar to number of neighbors for k-neighbors classifier, okay? So by playing around with gamma, we are creating those borders between the classes, either smooth or less smooth. If it is less smooth, it is more overfitting. If it is smoother, it is less overfitting. So let me tell about these two hyperparameters this much at this level, all right? Sorry if I got you confused. Okay, now let's define a hyperparameter grid. Okay, our parameter grid for grid search will be a dictionary, Python dictionary. So what does that mean? Let's see. First of all, this is the name of the dictionary. You can call it anything, my param grid, your param grid, you can call it anything. Okay, and then I'm just going to create a dictionary. A dictionary has keywords and corresponding values. And keyword value combinations are placed within two curly brackets, okay? And my first key value is my first hyperparameter, which is C. And you have some idea what C means here, right? All right, so I'm just going to write it this way first. Now I am giving different values for C. I'm giving a list of different values that C will be taken from, okay? So this is 10 to the power of, so this double asterisk is 10 to the power of. Now I'm gonna be using, so this is a NumPy array between the ranges of -3 and 3. So what is that? So it's going to create a range of list of numbers from -3 to 3. 3 is not included with step sizes of 1. Okay, if you make this 10 to the power of this, right? And this is what you're going to get, right? 10 to the power of -3, 10 to the power of -2, -3, -2, -1, 0, 1, 2. These are the values coming from this range here. And you are simply taking 10 to the power of that list. That's what we are doing. So these are the values. This list is holding the values that C would be taking. So this is my first hyperparameter. Okay, let me put the second hyperparameter, and the second hyperparameter is gamma. Again, gamma is like number of neighbors for my k-neighbors classifier, but in this case, gamma is the hyperparameter for the supervector emission. And gamma will be taking a similar again, you need to play around with these values too, but let me just take from 0, okay? So this is my param grid. So if you wonder how param grid looks like, okay, this is your param grid. It's a dictionary of my hyperparameters. C and gamma are keywords, and these two lists are the corresponding values. Well, you can create your param grid this way, or I mean, you can instead of using, so you can also do this. I'm just going to copy this. You can, if you like, you can, instead of writing this expression, if you like, you can simply use NumPy's log space. This will do the same thing. I just wanted to from -3 to 2. Okay, so what is this? NumPy log space, this one. It is creating a list of values in the logarithmic using the logarithmic scale, but you need to, this is the first value, this is the second value, you need to give also number of let's use 6 values. Okay, so we got the same thing, right? So between 10 to the power of -3 to 10 to the power of 2, I had 6 steps, 6 equal steps. Okay, 1, 2, 3, 4, 5, 6. 2 and -3 are included. If you like, you can do this too. Okay, it's the Same thing what we did earlier. The only thing is we are using logarithmic space function. Again, this is -5 and 0. I think with steps of 5. Okay, both will work, right? Both will work. Okay, this is our param grid. So let's continue. Once I have my parameters, the next thing is I'm going to create my grid search classifier, grid search object. So let's do that. My grid search, you can call it anything. Okay, my grid search, I'll be using grid search CV for that. Yes, I'm instantiating my grid search CV. Okay, now grid search is going to take estimator as the first parameter. What is my estimator? I'll be using SVC. I told you that, right? So this is my estimator. Okay, all right. And this estimator has two hyperparameters, C and gamma, and I'll be changing those hyperparameters, right? So I'm saying the name of the parameter is param under grid. So this is the name of the parameter. So you can simply say param grid. So this is the parameters that we created here. Okay. And lastly, you can say CV equals 5. This is cross validation, or if you like, we can create CV as we did here, like this. You can define CV outside and then put CV equals like CVK. Okay, this is my cross validation folds for 10 splits. But let's keep things simpler because we already have a combination of C and gamma, so let's make it just 5. Okay, so this is our, let me just get rid of this one. This is my grid search object. Let me just instantiate it. Okay, I'm now ready. I'm now ready to work on my grid search. Okay, so grid search is almost behaves like a normal classifier. I put a note here. So this is the object of my that I created for my grid search CV, which has SVC as the estimator, and these are the parameter values for 5 folds. Cross validation equals 5. So as whatever things I do for my classifier, I can do the same thing with my grid search CV. So let's do it. So my grid, okay. So I will take my grid search object, grid search. As I said, this acts like a normal classifier. A normal classifier comes with fit, predict, and score methods. So I can use fit method, fit on my trained data set. Remember, I'm fitting my model to my trained data, but when I am fitting my model, I'm not fitting a single model. I'm fitting multiple models. So each model will take a value from C and gamma, okay? Well, each model will take a value from C and gamma. So for each C and gamma combination, I'm gonna create 5 folds, means 5 different models. So in this case, I have 1, 2, 3, 4, 5, 6 C values, 1, 2, 3, 4, 5 gamma values, 5 times 6, 30 C gamma combinations. For each C gamma, I have 5 models, 30 times 5, I'm gonna have 150 models in total. I'll be creating, I'm fitting 150 models in total, okay. All right, so let's do it. That's why I said, I mean, you will have many, it's not practical to run a grid search over all different combinations of your hyperparameter values, right? It would be unrealistic to expect for large data sets, you know, to fit so many different models, right? But because we have a small data set, and then this is an example, I'm now fitting these 150 models on my trained data set. And then let's see what my grid is holding, what kind of information my grid is holding. By the way, let me check if you have any questions. Yeah, the Python notebooks are available on the Google Drive that I shared with you earlier. So you can see the link from earlier messages. Okay, I think I'm done with, okay, grid search is over. All right. So one thing I'm gonna do is I'm gonna turn this, so my grid here has, let me show you what my grid looks like, okay? Yeah, right now, actually, my grid is holding a lot of information. It's a grid search CV, which I created earlier. Okay, this is my estimator, this is my CV, this is my param grid. So let's turn this my grid CV results into a data frame. Okay, here's what I'm gonna do. Just let me import pandas. Sorry. And I'm going to turn my grid results to a data frame. Okay, you don't have to do it. I'm just going to show you something. Okay, that's why I'm doing that. Okay, let's turn this PD data frame. So my grid is returning the results of my cross validation for all these different models. How many models? 30 models. I have results for CV equals 5 for 30 models, right? And this is my grid. My grid is coming with this attribute called cross-validation results. So this is a built-in attribute coming with my grid, okay? But the moment you train your grid search object on your trained data set, the CV underscore results underscore is coming as an output, okay? So I'm turning this into a data frame so that I can work on it more conveniently, okay? More easily, okay? So I just turned it into a data frame, and then let's see what this grid results look like. I'm going to take a slice from this data frame, okay? As you know, for Panda data frame, when you take a slice, you can either refer to column names or you can refer to the indices of rows and columns. I'm going to refer to indices of rows or columns. I'm going to check the first 10 rows for all the columns. Okay, the first 10 rows for all the columns. You see, this CV results is holding a lot of information for us. So this is the first 10 rows. Actually, we have, I think we should have 150 rows, each row corresponding to a different C and gamma combination. And this is the test score for the split 0 for this combination. Remember, for each C and gamma combination, I will have 5 splits. This is the first split, split 0. The test score for the first split, test score for the second split and third split. So these are the test scores for the splits. And this is the mean test score. And this is the standard deviation of the test score. If you want to have the training scores as well, I think your grid search, when you are running your grid search, you need to set this. I cannot remember exactly now. I can check it for you, but set what is that? Train mean score equals true. That's what you should do. But let's not worry about it for now. Okay, this is what grid result DF is holding. So let's play around with that a little bit. Okay, so later on, I'm gonna play around with it a little bit later on. So let's do the predictions. Okay, again, grid search is already fit here, right? So fit. So I can make my predictions now, right? Grid search dot predict Now I'm making my prediction over my test data set, right? So when it makes the prediction, it's going to make the prediction using the best model. Remember, I had 150 models. It's going to use the best model when it makes the prediction, okay? All right, my predictions, if you want to see how your predictions look like, the first 10. So this is, if you want to print your score, so let's print the score. This is the placeholder, remember. Okay, and what is my grid search? Okay, again, remember what we did for earlier? I was using score method. I'm using the same thing, score method, for my test dataset as well as my test label. This is the score for this model here. So this is the score for the best model that I came up with for my test dataset. All right. Well, if you wonder what is the best parameters, it's easy. So you can grid search. So this is holding the best parameters. This underscore indicates this is an attribute that is computed as you are training your grid search, okay? So let's see. So these are the best hyperparameter combinations. C equals 1 and gamma is 0.001, right? C equals 1 and gamma equals 0.001, all right? Again, let's check the best score. Best score on your validation data set, okay? It's not, this best score is the best score on your validation data set, okay? As you see, my score on my test data set is even better than my validation data set. That means by changing C values, I actually reduce the overfitting, right? Normally you expect your, of course, you need to check your trained data set score too, but right now this is showing my best validation data set score. Okay. Best parameters. If you had multiple, it's possible that you might have multiple estimators. In this case, I have only one estimator, which is support vector machine. If you had multiple estimators, you could even check the best estimator with its best parameter values. I just had a chance to look at the comments. If you guys think that we are going fast and then losing the track of the code I'm writing, I'm doing my best to go as slow as possible. I can slow down a little bit more. After the class, let me save this and then upload it. By the way, I just arranged the Google Drive. I'm not going to change it that much anymore, so you will have access to all the materials from past weeks too. I can upload this file too, so that you can check it yourself and then try to work on it a little bit more on your own. Okay, one more thing is left here, so I just want to show it and then go to the next topic. Again, today, let me do this way, the pre-processing part. Let me also continue with hands-on on pre-processing without lecturing. So I'll do the lecturing. I'll start with lecturing next time and then do more hands-on as we do in the second part of the lecturing, okay? So I'll continue with hands-on on pre-processing today. But before getting into pre-processing, let me finish this. Just a small piece left. Okay, let's do this. I'm just going to do this. Let's say, let's take the mean of the test scores. Okay, so again, grid search. Right, grid search dot CV results. Remember, this is holding all this information. So again, if you like, you can play around with this. My goal was to show you that all this information is already here. So what I'm going to do is the results of my grid search, which is kept here, I am going to focus on my mean test score. Where is the mean test score? It's right here. So I'm going to focusing on this column, okay? Mean underscore test. Mean test score is the mean of the scores for my validation data set within my cross validation. So for each hyperparameter combination, I already created 5 models. And right, 5 models. Each model has a validation score and a train score. So this mean test score is the average of validation scores for 5 models for each hyperparameter value combination. Okay, so I'm just going to focus on my mean test score. Okay, again, this is the column corresponding to this one here. All right, so I just assigned these guys to scores variable. Okay, and then let me create an array of this. Okay. Before doing that, let's see what you're going to see with scores. Okay, so as you see, scores is holding all these mean test score values for different combinations of parameters, your hyperparameters. So let's go back here, look at here. Mean test score, this one is the test score, mean test score for C equals 0.001 and gamma equals 10 to the power of -5, right? And without changing your C value, now you are changing your gamma value, right? From 10 to the power of -5 to 10 to the power of -4, then to -3, then to -2, but you keep your C value constant. Then you change your C value and you restart from gamma equals 10 to the power of -5, then to 10 to the power of -4, then to 10 to the power of -3. So for you first set your C value and then change your gamma, and then change your C value and then change your gamma. Here, this is these 5 scores for a single C value. The next 5 scores is for another C value, okay? So scores is an array of those scores. So let me just create an array from my scores, a NumPy array, okay? Okay, now it's a NumPy array so that I can reshape this array. What did I do here? I took this guy here and then created an array with 6 rows and 5 columns. So let's see what happened now. Okay. What happened is, you see, this is the entire data set, but within the data set, I have almost like 1, 2, 3, 4, 5, 6 lists. Each list has 1, 2, 3, 4, 5 elements. That means each list is corresponding to, remember how many C values I had? C, 1, 2, 3, 4, 5, 6. For each C value, I have 1, 2, 3, 4, 5 gamma values. So that's why I did this. So each of these 5 element list is corresponding to one C value. Okay, that's why I took these extra steps and then create this reshaped array, okay? So why did I do that? I just want to plot a figure, color figure shows me how C and gamma values are changing. That's all. That's all. But I wanted you guys to understand why I'm doing these extra steps. Okay, now let's draw a color map, okay? For that, I'm using PLT. What is PLT? At the very beginning, I already imported PLT here. It's the abbreviation for matplotlib .pyplot. So this is the plotting library that I'm using, okay? This library has this match show, okay? So what am I gonna show? My scores, which I just created here. It's a array of 6 by 5, okay? And then, because this is gonna be a color map, so I will be using, there are different color maps available. I'll be using this one. Again, you can search for this, and then you can see that there are different color maps available. I'll be using this one, this blue color map, okay? So this is the name of a color map that I will be using when I'm plotting my scores, okay? You will see in a minute what I mean with that. Okay, now if you like, you can mark your X label and Y labels. So my X label will be gamma. My Y label will be my C. Okay, all right. Then if you like, you can also put the values of sticks on your figure. So that's what I'm gonna do. Not sticks, ticks. Okay. So the first one is y-axis, say x-axis, which has only 5 values. So I'm gonna say there are 5 values from 0, 1, 2, 3, 4. So I'm gonna put 5 ticks. Okay, and these ticks will be corresponding to, remember this param grid that I created. This was the dictionary. Remember this. I'm gonna take my dictionary's gamma values. Okay, so I'm going to have 5 ticks. Each tick will be correspond to 1 gamma value. Okay. I'm going to do the similar thing. So this needs some practice. Okay, so you can, I'm pretty sure you can figure it out. If you spend like 10 minutes, you will figure it out. This time, remember, I have 6 values, and instead of gamma, I'll be using C. Okay, all right. So I'm gonna show the color bar, which is gonna be telling me what color corresponds to which value. Okay, that's why I'm gonna be showing my color bar, and then it's time to show my figure. Okay, so let's see what it's gonna look like. So it's param grid, not param grid, I think. Okay, so this was the purpose of this piece of code. So what is this? This is the color bar. So the white color corresponds to what? 1, and this dark purple corresponds to 0. So this is my score. This is my gamma values, and this is my C values. So which gamma and C combination is giving me the best score? As you see, this region is giving me the best score. Remember, the best score value, it was C equals 1, gamma equals 0.001. So gamma equals 0.001 and C is 1. So this region right here, right? So it's the best scores. Again, this is the white color, which corresponds to score equals almost 1, right? So that was the purpose of this part. It's not very critical, but you know, just for your information, you can use some nice visual representation of your score in this way. And then I just wanted to let you know what each of these guys mean. Otherwise, again, you can change this color using different color maps, C maps, and then you can search for it. But again, these are the steps that we are taking when we are plotting this visual representation of our grid search results. All right, so let me go to the next one now, the pre-processing part. Again, I'm going to go through these steps, and then I'm going to explain each step, and we are gonna do the lecturing part next time, and I'll continue with pre-processing. There is a lot of hands-on stuff for pre-processing. After the lecture next time, I'll continue with pre-processing. So we have maybe 30, 35 more minutes, so let's begin with pre-processing. Let me check if there are any questions to this point. Okay. All right. So again, this is the library that you have. You have this file, right? I already shared this file with you. And let's first import this Boston house dataset from sklearn, scikit-learn datasets. Again, now we know what it means, right? Importing a dataset. So let's import it. Again, later on we are going to use our own datasets, but now we are using these toy datasets to instead of dataset itself, we are focusing on the steps, right? So that's why it is more convenient to use these datasets for now. So I'll be importing Boston datasets, and let's call Boston. Let's call this data equals my data. Load Boston. Okay, so okay, this is all right. So next thing is it says create, train, and test datasets. Now we know what this means, right? Again, from scikit-learn model selection, right? Import, train, test, splits. By the way, you guys got the file, right? Are you following me? I'm not doing this myself, right? Okay, I hope you guys are following. Yeah. Okay, thank you. So let's split the data sets. So let's call it X and Y as usual. Okay, so this will be my data and this my data. Whatever you called here, right? The label or targets. Okay. Okay, next I'm gonna create my train data sets. Test splits. What is that? X, Y. This is my data, this is my, and then let's all use the same random states so that we all will have the same split of data. Okay, so this is my train data set. Okay, so let's go to the step 2. So I have my train data set. So what is step 2 saying is let's create a scatter plot of each attribute with the mean house price. So if you like, you can this is a NumPy array, so nice. So this is how my data set looks like, but for now, I don't know what is what, right? So we'll see in a moment. We'll see in a moment. Let's see. This doesn't have feature name. Okay, because I created a NumPy array. All right. X might have this. sorry for the confusions, because when we load data sets, data set comes with an attribute called feature names. So I was trying to find feature names. These are the feature names of our data sets. Okay. If you wonder what these guys mean, you need to check the data description. So again, for scikit-learn data sets, each data set comes with a data description. So let me, if I'm not wrong, my data sets should come with something like this description. Yeah. So this is the crime per capita crime rate by town, for example. That's what it means. RM is average number of rooms per house. Full value property tax rate per $10,000. So these are the feature names of our data set. Okay. So where were we? Step 2 is we're going to create a scatter plot of each attribute with the mean house price. What is mean house price? Mean house price is this one, median value of owner-occupied homes, METV. This is my target variable. Okay, this is my target variable. All right, let's do it. For that, what I'm going to do is I'm going to create a figure. Okay, and then this figure will have these two components, and then I'm going to show you what it means. Remember PLT? I already created PLT, imported PLT earlier. So I will create subplots. Okay, so this subplots will have, it's going to be 3 by 5. So I will have 3 rows and 5 columns. And if you like, you can also use some figure size, like let's use 20 by 10. What does that mean? Let's just run this, and then just stop here for a while, and then see what this means. Okay, so as you see, I created 1, 2, 3, 4, 5 times 3, 15 figures. 3 times 5, 15 figures. That's why I have 3 rows and 5 columns, and each figure has a size of 20 by 10. So figure is corresponding to these guys. Axis will be corresponding to the methods and attributes of each of these figures. So what are those attributes like X label, Y label, the type of the plots I'm going to be using for each of these figures? That all will come with axis. Axis will have all these different attributes. There's so many attributes and methods that comes with axis. So if you want to see axis, it's an array of actually it's an array of objects. Each axis is an object. You see, this is corresponding to this figure here. This is corresponding to this figure. And as you see, axis is an array of 3 by 5. Okay, 1, 2, and 3. 3 by 5. 1, 2, 3, 4, 5. Each row has 5 columns. And each of these is one object, and each object corresponds to one figure. Each object comes with its own set of attributes. So if you wonder what kind of attributes they are, it's going to be long, but I'm just going to write it. So if you wonder what kind of attributes these guys are coming, I'm going to focus on this very first one. All of them are the same, but they're not different. So this dir is going to list all the methods and attributes of this first object here. Look at this one. Oh. Should have been around brackets. Okay. It's a long list of attributes and methods, right? It's a long list. Of course, I don't know what each one of these are corresponding to. We're just going to use a very limited set of these attributes and methods, but this guy has this, each object has this many methods. So let's just get rid of this. Okay, just get rid of it. Okay, So I just wanted you guys to know what we're doing, okay? Now I'll do one thing. I'm just going to get rid of these. So now, right now, it's an array of 3 by 5. I'm going to create an array of 1 by 15. Okay. For that, all I'm going to do is access. I will be using this label. Okay. So this basically is going to, it's nothing but changing my 3 by 5 array into an array of 1 by 15. That's all I did. Okay. With this one label. All right. So let's continue. Let me copy this. Come all the way here. Okay. Okay. Now I'm gonna loop through this axis. Okay. Remember, I have 15 of them. I'm gonna loop through this axis. So for, I'm gonna create a for loop. Okay. My internet connection says unstable, but you can still see on the screen, right? Okay. All right. Thank you. Thank you. Okay. Let's create a loop, and this loop will go through each of this figure. I will be corresponding to index of the loop, okay, and AX will be corresponding to this axis, okay. Enumerate. So when you use enumerate in for loop, what you're gonna do is you are going through these axes, and I will be corresponding to index of each of these axes. So index 0 means this very first guy. Index 1 means the second guy. Okay. So axis dot, well, now you know what this means, right? This means I took my 3 by 5 axis and turned it into a 1 by 15 array. And then I'm going through this array 1 by 1. I is corresponding to the index of each element of this array. Okay. All right. Now I have 15 figure, but I know that I have only 12. I need only 12 figures. So that's why I am saying if I is greater than 12, okay, because I have only 12 figures, 13 figures. If I is greater than 12, I'm just going to set my axis. This AX is corresponding to each of these figures, each of these objects. And remember, these objects are coming from with a rich set of attributes and methods. One attribute is set visible. So what I'm going to do is I'm just going to set this to false. Okay. But if I is less than 12, then it's going to be, it's just going to skip this. So what happens is if I is greater than 12, it's going to execute this, this line, and then we'll go back to the for loop. It's not going to do anything coming after this part, okay? So if you wonder what this does, let's just run this part. You see? So earlier I had 3 by 15 figures. Now I have only 13 figures. That's all I did now. So 1, 2, 3, 4, 5, 10, 13. When I is, this is I equals 12, this I equals 0. I equals 12, 13 and 14 are not shown. That's all I did here. Okay, let's continue. So let me go outside this if statement. Okay, now I'm gonna plot my figure, each of this figure. So for that, again, AX is corresponding to each of these figure. AX dot, I'm just going to plot. Okay, what I'm plotting is, remember my data sets. What is my data set? I already created my data set here. X is my data, Y is my label. Okay, so I will take my data sets, X, I. What is I? I is corresponding to the index 0. This I also corresponds to, the first column of my data set, which is the first feature. When I is 1, it's going to corresponding to the second feature, which I'll be using this figure here to plot my second feature. Okay. All right. So I'm plotting my ith feature from my data set with respect to my target variable, which is y. And I'll be using these rounds for each data point. And alpha equals 0.5 means you can, if alpha is if you can play around with this value to make, I mean, how the figure is going to look. I mean, you can change the tone of the figure by using alpha equals 0.5 or whatever. So if you simply run this part, this what happened, right? So each of these guys is the plot. This is the plot of the first feature with respect to your, I'm sorry, the first feature with respect to your mean house price, second feature with respect to your mean house price, third feature with respect to your house price. You look at the x-axis, they have very different range of values, right? Look at this one. This is 0 or 1. And look at this one, 0, 100. This is 2.5 to 12.5. So each of my features are coming with different range of values. That I have to take care of later, okay? We'll see that we need to take care of this later, all right? Let's do this a little bit look nicer. So I need to add my, what this figure is about, right? Let's add the title and also the labels, right? So let's add the label. So for that, I'm going to set my title. Let's set the title. So what is my title? So whatever you put here, it's gonna be so inside this brackets, it's gonna be a quotation. It's gonna be a text. So let's type that text. This is a placeholder. So this is a text with 2 placeholders. So let's say what these placeholders are for. The first placeholder is gonna be for I, which is the index like 0, 1, 2, okay? So I, the second placeholder will be about the feature name. So remember my data, all the way here, my data, load button. My data has one attribute called feature names right here. Okay, I'm gonna take this. I'm gonna take this, okay? I hope you guys are not bored up to this point. And I'm gonna take this, and this is the ith feature name, right? Feature name. So let's see what it does. See, I added my titles. Next, let's add the, let's add the labels for the y. We know what y is. This y-axis is actually corresponding to my target value. So my target value is, I know that it is median house price. So let's just add it. You can type anything here for label, y label. Okay, but I'm gonna type whatever the data tells me, median house price, MEDV, that is my label. Okay, that's what I'm gonna do. Okay, let's run this one more time. Okay, as you see, these are the features, and this is the label value. That's it. This, each of these is a scattered plot of median house price versus one feature. All right. So this is, we went through, we spent maybe 15 minutes on this figure. I think this is a good practice for plotting the figure, first of all, but my point is, before you do anything on your data set, okay, if possible, sometimes you will see your data set will have hundreds of features, but if possible, if there are some features that you see, or if you know the context that where data is coming from, if you know that some features are really, really relevant, I strongly recommend having these scatter plots of your features versus your target variable to see what kind of relationship. For example, look at this one. This guy has a non-linear relationship, right? So later on, again, as part of the pre-processing, maybe we're gonna turn this, whatever this variable is, turn it into some linear variable. Somehow, we're gonna transform it. Look at this one, number of rooms, home price. Clearly there is linear relationship, right? If you exclude this top part here. So as you have more number of rooms, the house price will increase. So this also shows some non-linear decreasing relationship. As there is more crime, right? The house price is decreasing, right? If there is no more, this again, whatever it is, more of that, the house price is decreasing. And you see some of the features are taking only 0 and 1, right? So these are like categorical variables, which we have to deal again later. This is more almost like a non-linear relationship. So for these non-linear ones, we need to make some transformations. Again, hopefully we're gonna learn later. Here, again, almost like a non-linear relationship, right? Almost. Okay, so these figures will help us visually see what kind of relationship each feature has with the target variable. Okay, let's do a similar analysis, this time doing box plot. There are different ways of creating box plots. I'm just gonna do one way. So PLT comes with its own method called box plots. It's very simple, so I'm just gonna do that one. So PLT dot box plots. Okay, and this is my data set. So let's see what happens if it's that simple. Okay, so each of these is corresponding to a box plot. Let's look at it. You can see. So I have box plot of my features, but I want to make this look a little bit nicer. So I want to know which feature, which feature this corresponds to. So I want to know that. So let's do a little bit more extra on this one. So let's add the X ticks, okay, on this one. All right. So I'm gonna add ticks. So how many ticks I'm gonna add? First of all, how many ticks? I will add this many ticks. Okay, how many? From 1 to, so these are the, it's gonna be from tick 1 to whatever value. If you put 10 here, I'm sorry, 1 to 10. So it's gonna be 1, 2, 3, 4, 5, up to 9 including. 10 is not included, right? How many ticks do I need? I need as many features as I have, right? As many, so I have 13 features actually. So how many features I have? This is my data set. This is the size of my data set, shape. So let me just show you what it means, shape, right? X.shape will give you the size of your data set. If you take X.shape 1, you are only focusing on the number of columns. There are 13 columns, okay? So, all right, but let's see what happens if I simply take this. Okay, so I'm creating a NumPy array of taking values from this range. Let's see. So as you see, 1, 2, 3, 4, 12. But I have 13 features, so I'm gonna add 1 in here, okay? So if you add 1 in here, remember the last one is not the last number, the closing point is not included, right? Okay, 13. So this is 14. This part is 14, 1 to 14. 14 is not included. The last point will be 13, okay? All right, these are the ticks. And then each tick will correspond to a feature name. What was my feature name? Remember my feature names? It was right here. I'm gonna take my feature names, okay? So I'm gonna put them here. Okay, these are my feature names. So each tick will correspond to a feature name. So let's see what happens if I do this. Yes, of these things. Okay, you see, these are my feature names. But as you see, the feature name is a little bit long. It is just overlapping with the next one. So can we just rotate this a little bit so it's gonna look nicer? Let me just do it, and we'll be done. Okay, rotation is you can pick any number. Let's say 30. Okay, let's do it. Yeah, it looks nicer. By the way, one additional thing that if you like, you can adjust the horizontal alignment of these feature names. If you say horizontal alignment is, in this case, our horizontal alignment is nicely came up with, but if you say let's center, the center was there, let's see. So centered, okay, no problem. If you say left, so you can align this, guys. You see, when you say left, it's a little bit overlapping with the text. So let's make it right. So it's gonna look better. Okay, so these are just they're just playing around. Okay, nothing very interesting. Okay, now let's look at this box plot. So remember when we were looking at this figure, I said some features are taking values from 0 to, in this case, 30, some of them 0 to 1, some of them 0 to 1, right? Some of them are taking really big values, right? So there are different ranges. So we can see this even better with a box plot. So look at this text. Text is taking so different, taking values from a really high range of values, right? And some of them is just taking values from 0 to 1. And so this midpoint here is indicating how symmetric the distribution of these data points. So this guy is not very symmetric, right? It is right skewed, right? And this is a little bit left skewed. This has a lot of, this is right skewed, right? So you may need to transform this data set later on to make it more symmetric looking, like moving this medium point here, if possible, by making some transformations. That is part of the pre-processing. Okay, so this is a very simple example. That's why you don't see very interesting, different types of range of values with really skewed data points. But still, we can definitely see that text is very different than this guy, and the age is different than this guy. So we have some features with very different values. So we need to take care of it using standard scalar. Okay, now let's talk about standard scalar a little bit. I have just enough time to do this step 4. I'll continue with step 5 next time. Yeah, I'll let me upload after I save it. If I forget, please use the Slack channel to remind, okay? So it's 4 a.m. here, by the way, so right after the class, I may forget. So, okay, so let's do standard scalar. Before writing the code, let me just show you what standard scalar means. We are taking a feature and we are subtracting mean of that feature from that feature. When I say feature, I'm referring to one column of my data set. So standard scalar does the following. Let's say X is my column, okay? Let's say X is my column. I am subtracting, so this is standard scalar, okay? What standard scalar does is, this is my feature. Let's say this is, in this case, text, okay? So I want to standard scale this one. Why? Because the range of values is really high. And when I do standard scaling, I'm gonna do standard scaling over all my numerical features. So what I'm gonna do is, I'm gonna take my text. When I say take my text, all the data points, all the values of corresponding to the text feature. X is representing all the data points all the values of text feature for all my data points, okay? And I'm subtracting mean of those values. If I have 100 values, I'm taking the mean of those 100 values and subtracting that mean from each of those values. So this way, I'm actually shifting my feature and center it around 0. So if you remember from statistics, if you take expected value of x minus x bar, if you take right, if you take expected value of x minus x bar, right? So this will be equal to 0, right? Sorry. Right, so because expected value of x is x bar, expected value of x bar is itself a number, just a scalar. So x bar minus x bar will be 0. So what I did here is by subtracting x bar from x, I am shifting my data points and centering it around 0. Next, I'm dividing x minus x bar by standard deviation of x. So what is this doing? What is standard deviation? Standard deviation tells you how much your data set is spreading around your mean value. If your standard deviation is small, your data set will be like this guy, or like this guy, or like this guy. Right? The standard deviation is small with respect to this one, right? So your data points will be spreading less around your data points are actually almost around your mean value. That is when your standard deviation is small. If your standard deviation is high, then your data points will be spreading around. This is your median point. Let's call it mean for now. Let's pretend that this is the mean point. This is the average of your data set. This is the average for this feature. If your standard deviation is high, the data points will be spreading around this average on a wide range of values. If your standard deviation is small, so this box will be squeezed, right? And then your data points will be centered, will be focused more around your mean value. So by subtracting x bar from x, you are shifting your data points, and then this feature, this particular feature will be centered around the 0 value. And when you divide by standard deviation, it's actually you are actually reducing the spread of your data. Actually, your variance of your data points now, after this division, this variance of this whole thing will be equal to 1. So by standard scaling, you are transforming your feature into a new feature with mean value equals 0 and standard deviation equals 1. And if you do this on every numerical feature, each of these transformed features will be a new feature with mean equals 0 and standard deviation equals 1. Okay, so let's take care of it. Care of it means let's standardize. Just type here. Okay, so what is standardizing? First of all, I need to import. Okay, again, Scikit-Learn comes with a pre-processing library. From pre-processing, I'm gonna be importing standard scaler. By the way, scaling has many different, 4 major scalars. We have different scalars. Standard scaler is one of them. It's the most standard one, okay? Standard scaler. Okay, standard scaler, I imported that. Similar to what we did with estimators. We have to instantiate our standard scaler. So let's do that. Let's call it scalar. You can call it anything, okay? Scalar. I am instantiating my standard scaler, okay? All right. So this guy, scalar, is now coming with the methods that will allow me to find this x bar and standard deviation of a particular attribute, okay, or a feature, sorry. Okay, now if like you can transform each feature individually, but I want to transform everything altogether, all the numeric features. So let's do it. I'm going to say X train scaled. Okay, I'm creating a scaled version of my train data set. So this part is critical. I'm going to explain why I'm using train data set here in my next lecture. Okay, just be patient. But I am scaling my train data set first. Okay, and I'm using my scalar object, which I just created. The scalar object comes with a fit and transform method. So fit helps me find X bar and standard deviation. Transform does this subtraction and division. Okay. Okay. I already scaled my train data set. Well, if you like, we can draw the same thing for my. Let's do this for train. Okay, and do the same thing for scaled one. Okay, and then see the difference. I didn't change these guys because all train X all have the same feature name, so that's why I didn't change it. Okay, this is my train data set, which is similar to my main big data set. Okay. Let's see what this guy does. This is my transformed data set. Look at text. Look my values. Look my features. Now they are all centered. You look at the center. So this is median. This is not mean. So mean and median will be different if your data set is skewed, right? But let's treat these guys close to. They will be close to mean value, right? So that's why look at them now. They are very close to 0. If I had used mean value for box plot, they would be all aligned at 0. And then as you see, the spread is more under control now. The spread is between is actually -1 and 1 almost. Okay, you still can have more than 1 and -1, but 85% of your data points will be within -1 and 1. 95% of your data points will be within 2 and -2. Okay. So I not only centered my data points, each of my feature, but I also reduce the spread so that my data points are squeezed in between, mostly in between -1 and 1, 85% of them. So that is scaling, standard scalar. Let me continue with this in the next lecture. I'll explain why we are doing this. This is very important. This part is very important. If you are new into machine learning, this part is very important. I'm going to explain, and later on you'll see that we're going to create pipelines that will take care of this scaling very conveniently, and then hopefully we're going to see that maybe next lecture, maybe next lecture. I'm not sure now. Okay, so let me stop here. Okay, we'll continue next time, and hopefully, if I don't forget, I'm going to upload the saved. Let me just save here, the saved one to the Google Drive right after the lecture, so that you can access. Okay, thank you guys. Talk to you next time.